Hi everyone. All right, so in order to derive the OLS estimator in the multivariate case, we start with the same definition for the OLS estimator, which is the minimizing or the set of parameters that minimize the sum of squared residuals. And so again, we're starting with beta hat being equal to the beta parameters, the set of beta parameters that are in that vector beta that minimize the sum of squared residuals, which is the difference between yn, the observed yn, and beta prime xn, which is now just the vector form of this linear model squared and then summed over all observations, right? So this is the same specification of the sum of squared residuals now in the multivariate case using the vector form of the linear model, okay? Um, we could also uh, we could also specify this in using the matrix notation. In the matrix notation, rather than writing the sum of squared residuals as yn minus beta prime xn squared and then summing over all observations n, we would just look at y bar minus x. Sorry, not y bar. Y vector minus x beta prime times y vector minus x beta vector. Okay, so if you look at these two, um, or if you look into the parentheses, first this is a one by sorry, an n by one vector. X times beta will be a 1 by n vector as well. So this is a 1 by n vector. We transpose that. So this becomes, sorry, this is an n by 1 vector. X beta becomes an n by 1 vector as well. So the transpose of an n by 1 is a 1 by n vector. So a 1 by n vector times an n by 1 vector is just a scalar, right? So this specification, if you kind of go through the rules of matrix multiplication, you will see that this specification, y minus x beta prime times y, or matrix multiplied y minus x beta, is exactly the same specification that we have up here, right? We have a row vector times a column vector, so that means we're just multiplying each individual element and summing them all together. That's equivalent of taking the square of this term and summing them all for all observations, right? So it's the same equivalent specification, one again using the vector notation and one using the matrix notation, right? If you're unsure, maybe go through this, using a minimal example of like 3 observations and 2 parameters, and just multiply out those matrix multiplications, and then you'll see that you'll end up with the same result. It's just a different representation of the underlying model. Okay. So focusing on the vector form, so the part up here, we can now again just take the first order condition. So we take the first derivative with respect to each element in beta, and we have to set that equal to 0, right? So this is just exactly the same thing that we've done in the bivariate case, now just for multiple betas, right? And so if we take this specification and we take the derivative of this term with respect to beta, we again use the same chain. We have to use the chain rule again. So that's 2 times so this is the derivative of the kind of outside function times the derivative of the inside function. And so this is, of course, the outside function is just square, so this is 2 times what is inside the parentheses, and then times the derivative of the inside function, which is just partial derivative with respect to beta of this term again, right? So this is just applying the chain rule right here to the term that we have up here, okay? Now again, just kind of transferred into the vector notation, okay? And if we take the derivative of this term with respect to beta, then of course this just reduces to xn, right? So the derivative, this last part here, reduces to, because yn is a constant, the beta vector prime, that's the derivative that we're taking the derivative with respect to that beta vector, so that drops out, or well, it turns into 1, so 1 times xn is just xn, so all that is left is this xn vector. So that's the first derivative of the linear model, or of the sum of squared residuals with respect to beta, okay? And it's important to kind of recognize, if we kind of and you know, you might not be so used to taking derivatives of, you know, vectors or partial derivatives, but if you go through kind of a minimal example of the specification, it's important to notice, if you reduce this, for example, to a bivariate case with one intercept and one beta parameter, then this specification of this first order condition of the beta vector basically implicitly combines our previous equation for the intercept and slope that we had before. Try, like, in a kind of go back to the slides or the video where I derived OLS in the bivariate case, and compare those two or those two equations with this kind of vector specification, and you'll see that the vector specification kind of combines the two individual first order conditions that we derived for alpha and beta, okay? So in other words, our OLS estimator has to satisfy, and again we can get rid of this -2 as we did before in the bivariate case, and divide by n, and then this becomes 1 over n equals 1 through n, the sum of yn minus beta prime xn times xn, and that has to be equal to 0. And that, solving this now for beta hat, will provide us with the formula for the OLS estimator, because that will be those will be the values for beta hat that minimize the sum of squared residuals as we kind of set them up or define them up here, okay? So how do we do this? We're here in this equation, and the first thing that we want to do is we want to multiply out the product that we have here, right? So this xn will be multiplied out, and so that means after we're doing that, we can also separate the sum, 1 over n times n equals 1 through n, the sum. We can separate those for both elements, so we're left with the sum of yn minus xn vector minus beta hat prime x times xn times xn, okay? So this is just multiplying out this product here and then separating these sums, and that has to be equal to 0, okay? Now we have to use a couple of tricks to rearrange this equation, and remember that one of the things that we mentioned, whenever we have matrix multiplication, then the order really matters, right? If we have two matrices A and B, A times B is not necessarily equal to B times A, right? So we can't just rearrange the elements of a product, right? But we can do some tricks to rearrange this equation. And in order to use these tricks, you have to recognize here that this equation beta hat prime times xn, that is a scalar, why is this a scalar? Well, beta hat prime is a 1 by a 1 by k matrix, right? So it has one row and k columns. Xn is a k by 1 matrix, so it has k rows and one column, right? If going back to these rules of matrix multiplication, multiplying a 1 by k matrix times a k by 1 matrix, the result will be a 1 by 1 matrix. So in other words, it will be a scalar. It's just a single number, right? If beta prime xn is a scalar, it's just a single number, then we can just move it around, right? Because scalar multiplication, as compared to matrix multiplication, the order doesn't matter, right? So if we kind of treat beta prime xn as one unit, we can move it around in our product, right? So what we're going to do here is we're going to take this beta prime xn and we're going to move it to the end, right? So this is what is happening here. We just took this beta prime xn and moved it to the back here, right? No math has been broken. Everything is still fine. The equation still holds, okay? Now there's another trick, and this is another kind of matrix rule that we talked about briefly, which is that the transpose of a scalar is equal to the original scalar, right? So if I take, of course, the transpose of a matrix switches the dimensions of columns and rows, right? But if we have a scalar, so an individual number, a 1 by 1 matrix, taking the transpose of that is still the same matrix, right? So that means we can take this beta prime xn and take the transpose of that, and that's still the same exact number, right? If we take the transpose of that, however, so this is now just taking the transpose of this part back here. If we take the transpose of that, however, remember that we can, if we take the transpose of a product, we can kind of solve the transpose, and the rule in which we kind of solve that transpose of that product is that we have to switch around the order of those two elements, right? So the rule was here that if we have two matrices, A and B, and we matrix multiply them, so A times B, and then we take the transpose of A times B, that is equal to B transpose A transpose, right? We can take the transpose of the individual elements, but we have to switch their order, right? So this is what we're going to do. We take the transpose of this B prime xn, and in order to take that transpose, we have to switch their order and then take the individual transposes, right? So that means xn prime will come to the front, and beta hat prime, and then prime again, so twice the transpose is of course back again to the original beta. So we're here, we now have beta hat vector at the end of this equation, okay? So this is now x times xn prime times beta hat. And this is now just rearranging this equation, just using two kind of tricks of matrix algebra to move this beta hat from the front to all the way to the back. And for this to work, ultimately what we'll have to do is we have to kind of transpose this one xn here. But this is kind of the intermediate steps that are happening in between, okay? Why do we need this? Why is this useful? Well, this is useful because now what we can do is we have isolated our beta hat vector on the right side of the equation, and we can treat all this stuff as one unit and put it on the other side, okay? If we put it on the other side, what we can do is we can just multiply both sides of this equation by the inverse of this term, so this term to the power of -1, to basically cancel this out and add it on the left side, right? We did this already in the scalar case. This is now just a little bit different in the context of vectors, but the idea is the same. we multiply by the inverse of this term on both sides, which means this moves to the other side. Okay, and in order to do this, in order to take that inverse, this is kind of going back to what we talked about with matrices having full rank, right? Um, so first of all, maybe xn times xn prime is a matrix, right? That's the first thing to kind of recognize. Xn, as I said, is a k by 1 matrix, and xn prime is a 1 by k matrix. So the product here is actually a k by k matrix. If we want to take the inverse of that and multiply it by the inverse on both sides, we need to be able to actually take, or in order to kind of put this on the other side of this equation, we need to be able to take the inverse of this matrix, right? And remember now, going back to matrix inverses, that requires that this matrix is a full rank, which means that the matrix has to be invertible, which, you know, going back to what we talked about, means that all the rows and columns have to be linearly independent. What does it mean for them to be linearly independent? Well, none of the rows or none of the columns can be a linear combination of the other rows that are included in that matrix, right? And so this is one of the crucial kind of like in the underlying matrix algebra, why you can't run an OLS model with two, the same variable included twice, or one variable being a perfect, or two variables being or one variable being kind of a linear combination of the other sets of variables. As soon as you have perfect correlation between one variable and another variable or a set of other variables, what OLS is doing is what the linear model function in R is doing is dropping one of those variables, right? But the underlying reason why that is necessary is ultimately that this xn prime matrix doesn't have full rank. It's not invertible. We can't put it on the other side, so we can actually derive our beta hats that minimize the sum of squared residuals, right? So this step, an xn prime having full rank, is directly related to this requirement of the absence of perfect collinearity between the x's, right? That's an important point to kind of recognize. If xn prime has full rank, so if this matrix is invertible, and so all the vectors or all the columns and rows in xn prime are linearly independent, then we can put this on the other side, and we're left with beta hat vector being equal to 1 over n sum n equals 1 through n of xn prime inverse. So now this is the matrix inverse times 1 over n equals 1 through n of xn yn, which is just the expression that we had here on the left hand side, right? And now this is in vector form. We can also kind of specify this back in matrix form, which is x prime, now the x matrix, not xn vector, x prime x inverse x prime y. So this is the compact matrix specification of the OLS estimator. This beta hat vector contains now the intercept and all the beta 1, beta 2, beta 3, and so on up to beta k that are included in our model, right? And you can directly see, if you kind of followed the kind of jumping from the vector form to the matrix form, this is again the same kind of equivalent expression. 1 over n sum of xn prime is equivalent to taking the entire x n by k matrix, and since x is an n by k, x prime is a k by n, so k by n times an n by k, this is again a k by k matrix that is exactly equivalent to this expression up here, and we take the inverse of that, and then x prime, and then multiply this by x prime y. This is equivalent to this part again. The 1 over n, of course, can be dropped. I mean, ultimately, this is 1 over n divided by 1 over n, right? So it disappears, right? And this is kind of the one equation that you have to remember to compute OLS is x prime x inverse x prime y. Okay. All right, that's already it for showing or kind of deriving the OLS estimator in matrix form. In the next video, I'm going to show you how to program this in R.